If you've ever played sports, there's a good chance that you've had to spend a lot of time running stadiums as part of your training. I know I've spent countless hours going up and down various flights of stairs. And if you're mathematically inclined, your mind might start to wander. And eventually you might distract yourself from the physical pain brought on by this coach-imposed torture with a math problem. For example, if you were running up 20 stairs and could climb the stairs 1, 2, or 3 at a time, you might wonder how many different ways you could make it to the top. So to be clear, I would call 2 ways the same if you touch the exact same stairs on those 2 journeys to the top. Turns out this is a pretty interesting math problem that can be solved a number of ways. When I first saw it, I thought to use a combinatorial method, which works fine, but it's a bit arduous. I later learned that you could solve it by recursion, which is quite a bit easier if you're clever enough to see how to do it. In this video, I'm going to take you through both ways. To get a feel for the problem, let's change some numbers and assumptions to make it a lot easier. Instead of 20 stairs, let's just deal with 6 stairs. And instead of taking them 1, 2, or 3 at a time, let's suppose we can only take them 1 or 2 at a time. If we let 2, 1, 1, 2 represent the journey where we first take 2 steps, then 1 step, then 1 step, then 2 steps. So we start by going to the second step, then to the third, then to the fourth, then all the way up to the sixth. We could probably just enumerate all the different journeys to the top of the stairs. You might want to pause and see if you come up with the same list that I come up with. To make sure that I don't miss any, I'm going to sort my list by the number of 2s. So if I didn't have any 2s, that means I'm taking all the steps 1 at a time. So I denote that journey as 1, 1, 1, 1, 1, 1. If I had 1, 2, that 2 could be at the start, somewhere in the middle, or at the end. If I had 2 2s, that's accounting for 4 of the 6 steps, so I guess I'd need 2 1s. It's a little annoying to enumerate all the ways you can list 2 2s and 2 1s, but if you're willing to spend a couple minutes and impose some sort of logic in your order, I bet you can come up with these 6. And then finally, if I have 3 2s, that's getting me all the way to the top, so I don't have any 1s. So the final element in my list is just 2 2 2. So to answer this question, we just have to add up 1 plus 5 plus 6 plus 1 to get 13 possible ways to get up 6 steps if we could take those steps 1 or 2 at a time. But really the purpose of this easier question wasn't to get the answer, but to understand how to get the answer. So here you might notice that if you sum the digits of any of these elements, you get 6, which makes sense because it's 6 steps we have to get up, and that the element in the no 2s column has 6 digits in it, and as you move columns, each time you get an extra 2, you lose 1 digit because essentially you're trading 2 1s for 1 2. So the elements in the remaining columns have 5, 4, and 3 digits respectively. So with that information, could we figure out how many ways there are to climb 6 stairs if we're taking the stairs 1 or 2 at a time without actually enumerating all the different possibilities? Yeah, I think so. I mean, if there's 6 stairs, it's easy enough to see that we can either have 0, 1, 2, or 3 2s. And once we know how many 2s we have, we know how many digits there are in our code. And in a previous video, we learned a method that told us how to figure out how many unique ways we can arrange a given number of heads and tails. We can do that same method here to figure out how many ways there are to arrange a given number of 1s and 2s. So for example, in the 4-digit column where we have 2 2s and 2 1s, we can just count how many ways there are to arrange the 2s, knowing that we'll fill up all the remaining blanks with 1s. So we have 4 options for where to put the first 2, and then 3 options left for where we'll put the second 2. So you might think there should be 4 times 3 or 12 items listed in this column. But there's not, because the 2 2s are indistinguishable. So for example, if we put the first 2 in the second spot and the second 2 in the fourth spot, that would be identical to putting the first 2 in the fourth spot and the second 2 in the second spot. So we have to divide the 12 by the number of ways we can shuffle up the 2 2s. Well, there's 2 ways to shuffle the 2s, because once you've fixed which blanks they're going in, you have 2 options for which 2 goes in the first blank, and then just 1 left for the 2 that goes in the second blank. What I'm saying is, because this column has 4 digits with 2 2s, there should be 4 times 3 divided by 2 times 1, or 6 elements in the column, which we saw when we enumerated them. To make this more formulaic, we can think of 4 times 3 divided by 2 times 1 as 4 factorial divided by 2 factorial times 2 factorial. Or more generally, if we want to know how many different ways we can arrange A 2s and B 1s, it would just be A plus B factorial divided by A factorial times B factorial. So even without enumerating our lists, we'd know that if there were 0 2s, then all 6 digits would be 1s, so A would be 0 and B would be 6, and we'd calculate just one way to arrange these digits. If there is 1 2, there'd be 5 digits, so 4 1s. A equals 1, B equals 4. If there's 2 2s, there's 4 digits, so there's 2 1s, and if there's 3 2s, there's only 3 digits, so there's 0 1s. The point is, without enumerating, we could still calculate the number of elements in each of these different columns. So we could figure out there's 13 unique ways to get up these 6 steps, taking steps 1 or 2 at a time, without listing them all out. And that's a big deal, because in the real problem, there's not 6 steps, there's instead 20 steps. And you certainly wouldn't want to enumerate all the possibilities here, but we can follow a similar method to calculate how many possibilities there are. If we had 0 2s, then all 20 digits would be 1s, so A is 0 and B is 20. If we had 1 2, then we'd have 18 1s, so when A is 1, B is 18. 2 2s would leave 16 1s, 3 2s, 14 1s, and so on until we get all the way down to 10 2s, leaving us with 0 1s. It's kind of a mess. Arduous is how I described it before, but it wouldn't be hard to figure out with the help of a calculator. But unfortunately, I have to point out that we're still answering a simplified version of the original question. We're supposed to allow the athlete to take steps 1, 2, or 3 at a time. But what you'll see is that change doesn't add too much to the problem. We just need to notice that if there's 20 steps, then there can be anywhere from 0 to 6 threes in our code. So we can think about the number of threes defining 7 different cases. If we have 4 threes, for example, that's 12 steps. So we have 8 steps left for the 1s and the 2s. So if there's 4 2s, there's 0 1s, 3 2s, there's 2 1s, 2 2s, there's 4 1s, 1 2, there's 6 1s, and 0 2, there's 8 1s. Since there will be 1s, 2s, and 3s in our code, we'll need a slightly more generalized formula for the number of unique arrangements of these digits, but then it just becomes an exercise in plugging numbers into a calculator. We can repeat the same logic for the 6 remaining cases, add up all the numbers, and get our answer in a rather uninspiring fashion. However, as is often the case in mathematics, getting the answer shouldn't be viewed as the finish line. As I alluded to earlier, there's a much more satisfying way to get there. Let's go back and re-examine the simplest of the cases we've seen, where there's only 6 steps and we take them 1 or 2 at a time. To come up with a recursive solution, we're going to partition our 13 codes into 2 groups based on the last digit of the code. In other words, there's only 2 ways our athlete can make it to the top: by making it to the 4th step and then taking 2 at a time, or by making it to the 5th step and then taking the last one at a time. Hopefully you can convince yourself that this will account for all possibilities and won't double count any of them. Let's first take a look at the column containing the codes that end in a 2. Because they end in a 2, we're always going to go from the 4th step to the 6th step, so the only thing that can change is how we get to that 4th step. What I'm saying is really all this column does is list all the possible ways to get to the 4th step and then tack on a 2. So the number of elements in this column just corresponds with the number of ways we can get up 4 steps, taking them 1 or 2 at a time. Similarly, in the column containing codes that end with a 1, that final 1 means we're always going to go from the 5th step to the 6th step, so the only thing that can change is the way we get to the 5th step. So the number of elements in this column will correspond with the number of ways we could climb 5 stairs if we took the stairs 1 or 2 at a time. What I'm saying is the number of ways you can climb 6 stairs if you take them 1 or 2 at a time is equal to the sum of the number of ways you could climb 4 stairs if you take them 1 or 2 at a time, and the number of ways you could climb 5 stairs if you take them 1 or 2 at a time. And maybe you're like, yeah, but how do we know how many ways we can climb 4 and 5 stairs if we take them 1 or 2 at a time? Well, by the exact same logic, the number of ways we can climb 5 stairs would be equal to the number of ways we can climb 4 stairs plus the number of ways we can climb 3 stairs. What I'm saying is we have a sequence where each element in the sequence is equal to the sum of the 2 elements prior, and because there's only one way to climb 1 step, and there's 2 ways, 1, 1, or 2, to climb 2 steps, we have the Fibonacci sequence. Okay. Anyway, since most people think of the Fibonacci sequence as starting with 2 1s, although it never really starts or ends, I guess our values come from a shifted Fibonacci sequence. So to figure out how many ways we could get up 20 stairs, taking them 1 or 2 at a time, we just take the 21st element in the Fibonacci sequence. It's worth pointing out, since we figured out an ugly formula that would get these values earlier, I suppose we now have an ugly formula that generates the values of the Fibonacci sequence. Although, like everything I stumble across in math, I'm sure this was discovered long ago by someone far smarter than me. On the one hand, we're still answering simplified versions of the original question, which was how many ways can you climb 20 stairs if you could take them 1, 2, or 3 at a time. However, on the other hand, I think all the work we've done on these simpler versions has set us up well to finally answer this question. Could you do it? If we're taking the stairs 1, 2, or 3 at a time, either we make it to the 17th step somehow, and then jump the last 3 to the top, or we make it to the 18th step and jump the last 2, or we make it to the 19th step and finish by just taking a single step. Convince yourself that this accounts for every single possibility and doesn't double count anything. And you might be like, wait a minute, what if I make it to the 17th step and then just take 2 and make it to the 19th step? Wouldn't that get double counted? And the answer is no. That would fall into our third case where we make it to the 19th step and take the final step just 1 at a time, but not under our first case, because in our first case we go from the 17th step all the way to the finish. So if we were to take the time to list out the 121,000 some ways that we could make it to the top of 20 steps if we took them 1, 2, or 3 at a time that we calculated earlier, we'd see that every code either ends in a 1, a 2, or a 3. And the ones that end in a 1 just correspond with all the different ways we can climb 19 steps and then tack on a 1. And the ones that end in a 2 would correspond with the number of ways we can climb 18 steps. And the ones that end in a 3 would correspond with the number of ways we can climb 17 steps. What I'm saying is the number of ways we can climb 20 steps if we're taking the steps 1, 2, or 3 at a time is just the sum of the number of ways we can climb 17 steps, taking them 1, 2, or 3 at a time, the number of ways we can climb 18 steps, taking them 1, 2, or 3 at a time, and the number of ways we can climb 19 steps, taking them 1, 2, or 3 at a time. We've got another sequence, but this time the elements in the sequence aren't the sum of the 2 previous terms, but instead the sum of the 3 previous terms. I thought I'd be really funny and call these Tribonacci numbers. Unfortunately, not only does this sequence already exist, but somebody else named it the Tribonacci numbers. I guess I'm not as clever as I thought. Since we're summing the 3 previous terms, we need to calculate by hand the first 3 terms to kind of get the ball rolling. There's still just one way to get up 1 stair, and 2 ways, 1, 1, and 2 to get up 2 stairs. But to get up 3 stairs, we can go 1, 1, 1, 1, 2, 2, 1, or 3. So there's 4 ways to get up 3 stairs. We don't have to list out how many ways there are to get up 4 stairs because we can just add up the 3 previous terms in our sequence. We can continue in this fashion for a little while and you'll see that the numbers start to get pretty big pretty quick. By the time we get to 17 stairs, we see there's 19,513 ways to get up them. And for 18 and 19 stairs, there's 35,890 and 66,012 ways. So to answer our final question, we figure out how many ways there are to get up 20 stairs, taking them 1, 2, or 3 at a time by adding up the answers we got for 17, 18, and 19, and once again see that there's 121,415 ways. Similar to how we related the 2 different methods to come up with the combinatorial formula for the Fibonacci numbers, we could relate our 2 different methods to come up with the combinatorial formula for the Tribonacci numbers. Most people think of this sequence as starting out with 0, 1, 1, 2, 4, 7, although much like the Fibonacci numbers, they don't really ever start or end. What that means is most people would call our answer the 22nd Tribonacci number, which we could calculate explicitly, because remember earlier, we used this formula to answer the same question. I'm not going to bother extending this to try to calculate a general combinatorial formula for the Tribonacci numbers, but if that's something you're into, I'm sure you could figure it out. Instead, I'm going to call this video good and leave you with a challenge question. Much like the main question of this video, the challenge question asks how many ways you can get up 20 stairs. However, now you got crazy leaping ability and can take them any amount at a time as you want. So you go all the way from the bottom to the top in one big jump, or take all 20 steps one at a time, or anywhere in between. If you can figure it out or have any questions or thoughts, throw them in the comments.